Okay, the next section 9.4 is on sequences. So we'll do some infinite sequences, we'll do limits, arithmetic and geometric are our main ones. We'll use the calculator to help us out with these. And this is kind of the fundamental concept of calculus when we get into infinite sequences. This is kind of the key concept, as we're going to find out. So a sequence is the most natural way to study patterns. It's just an ordered progression. We can have finite sequences which have a fixed number of terms. We can have infinite sequences which have an infinite number of terms. All right, we can talk about the limit of a sequence as our n goes to infinity. So as we go to a larger and larger number of terms. All right, if it converges, there's going to be an actual limit. If it doesn't, it's going to go off to infinity, and we say that diverges. So here's an example then. Our sequence is 2 over n, which, never mind if that's arithmetic or geometric for now, but it's actually neither. But anyways, to find the first term, we plug in 1 for n, you get 2. To find the second term, we plug in 2 for n, you get 1, and so on. So the question is, as this thing goes off to infinity, does it converge, and if so, give its limit. As it goes off to infinity, you can tell this bottom's getting bigger and bigger, so it is going to 0. So the limit of this thing, I can say the limit as n approaches infinity of this sequence 2 over n is 0. Okay, the first type of sequence we're going to look at in detail is arithmetic. Arithmetic, basically you're just adding a constant d each time. So d is the common difference, we call it. And here's the formula that we can use then. It's just like a linear formula where I put it on the formula sheet like this. A sub n equals the first term plus n minus 1 times the common difference. So here's an example then. We can find the common difference for part A. The common difference is we are adding 3 each time. So d is 3. If we want to find the 10th term, I'm actually going to skip ahead and write an explicit rule. So I'm going to do part D first. And we have on the formula sheet a sub n equals the first term plus n minus 1 times the common difference. So the first term is negative 2. N minus 1 times the common difference is 3. And I can simplify this a little bit if I write it as negative 2 plus 3n minus 3. And I guess I can simplify it a little bit more if I write it as a sub n equals, and add the negative 3 and the negative 2 to get negative 5, so 3n minus 5. So there's my y equals mx plus b almost, only we're not using all numbers, we're just using integer values here for n, whole numbers. So I can use this then for part B when it wants to find the 10th term, just plug in 10 here. 10th term would be 10 times 3, which is 30, minus 5 is 25. So if I want, I can say the 10th term is 25. And then C wants a recursive relationship. Recursive relationships, we start with the first term is negative 2. And then we say, okay, well then the nth term is what in relation to the previous term? So the nth term then is the previous term, I'll call that a sub n minus 1, and we're adding 3 to that each time. So there's our recursive relationship right here. And if part D we already did, the explicit rule is right here. Okay, our next main type of sequence is geometric. Geometric, we're just multiplying by r each time. So take the first term, multiply by r, and then multiply by r again to get each successive term. That r is called the common ratio. Here's our formula. I wrote it on the formula sheet like this. The first term times r to the n minus 1. So here's an example of that then. If I want to find the common ratio for this one, for example, I'm multiplying by 3 each time. So my common ratio is 3. Part B, if it wants to find the 10th term, I'm going to skip ahead again to part D, where I'm going to write the explicit rule, which is the first term times r to the n minus 1. First term is 2, r is 3, so there's my explicit rule, and I can use that to find the 10th term. The 10th term, I plug this in, and I get 2 times 3 to the 9th, so it's 2 times 3 to the 9th, which I'm going to have to do in the calculator, which gives me 39,366. Then C, a recursive rule. A recursive rule says we're going to start with what is the first term. The first term is 2. And then it's going to say, what do you do to the previous term to get the next term? So the previous term would be g sub n minus 1. I'm just going to multiply that by 3 each time to get the next term. So there would be my recursive relationship. Okay, here's an example of constructing a sequence where we're not told if it's arithmetic or geometric. But it does say the third and sixth term. So the third term is 48. So I'm like making a table for g, or for n and a sub n, or G sub n, whatever you want to call it. And the sixth term is 6. So it's definitely getting smaller here. The question is, are we subtracting something each time, or are we adding something or multiplying by something each time? Well, let's assume that we're arithmetic here first. So for part A, assuming we're arithmetic, we have 4, 5 here. So we're subtracting something each time to get to the sixth term. So we start with 48, and we subtract the common difference a certain number of times. It would be 1, 2, 3 times. So 3 times the common difference to get to 6. All right, another way is we can just plug it into the formula that we had. A sub n equals the first term, which actually, I'm sorry, we don't really know the first term. So let's just use what we did here. So subtract 48 from both sides and divide by -3, and you get a common difference of -14. So that would be, this would be 34, and this would be 20. You're subtracting 14 each time to get to the next term. So if we wanted to write an explicit relationship for that, that would be a sub n equals the first term plus n minus 1 times the common difference. We now know the common difference is -14, but we don't know the first term. So I'm going to plug that in along with one of these ordered pair in order to find the first term. So I'm going to plug in 48 here. First term is, plug in 48 here. First term is what we're looking for. And n is 3 in this case, so it'd be 2 times -14. So I can solve for the first term now just by adding 28 to both sides. And so the first term must have been 76 if we use it this way. So our formula would be a sub n equals 76 plus n minus 1 times the common difference of -14. And that's good enough for me. You can simplify it by distributing and rearranging, but that's good enough for me. So, and if we wanted to write a recursive relationship, that's where we start with the first term, which in this case is 76. And then we say, what are we doing each time? Well, to the previous term, we're subtracting 14 to get the next term. So there's our recursive, and there's our explicit. Now the next one is for geometric, so now I have to start over. For geometric, we'd have g sub n equals the first term times r to the n minus 1. So we have to look at, if we're multiplying by r each time, what do we get? Well, one thing we can do is to say that we're taking 48 and we're multiplying by r 3 times, so it'd be r cubed, and we're getting 6. And now that will help us find the common ratio if we divide by 48 and take the cube root. And if we do that, we get r equals 1/2. So what I'm doing each time is I'm multiplying by 1/2. So that's my ratio 1/2. And I'm going to have to work backwards to get my first term. So if you want, to go backwards, obviously, instead of multiplying by 1/2, we can multiply by 2 and go backwards too. That's probably the easiest. And that gives us, 96 here and 192 here. Another way to do that is use this formula right here. Take like 348, which is what they gave us, plug in 48 for g sub n, plug in 3 for the third term, so it'll be 1/2 to the second power then, 3 minus 1, and then solve for the first term. If you do that, you get 192 again. So if we write out our formula, it's g sub n equals the first term 192 times the common ratio 1/2 to the n minus 1 power. There's the explicit. If we want to use the recursive, then we could say g sub 1 is the first term, which is 192, and then each time to get the next term, we are taking the previous term and we're multiplying by 1/2. Okay, a really interesting sequence to look at is the Fibonacci sequence. I strongly recommend you look at this. You can start writing this out. The first term is 1 and the second term is also 1, and then to get the next two terms you just add the previous two together. So add these previous two to get, second term. The third term you'd add these and get 2. The fourth term you'd add these and get 3. The fifth term you'd add these and get 5, and so on. All right, and this sequence has just incredible application. It turns out that, like, for example, these ratios exist in your body. It turns out that they exist in all kinds of places in nature. Like plants grow a certain number of leaves in these arrangements to basically maximize the amount of sunlight they can collect. So there's gross evolutionary pressure on plants to do this, because the ones that do it will have an advantage to collect the most sunlight and convert the most energy through photosynthesis, obviously. And the ones that don't do this will not be at an advantage, so not as likely to carry on their genes, so to speak. So I strongly recommend this. If you YouTube Fibonacci sequence and check this out, this girl, Vihart, makes a series of 3 videos here where she explains that in a much more detailed way than I just did. This is a decent one too. I mean, just as far as, you know, the imagery and whatnot. But it turns out the Fibonacci sequence, the golden ratio, these exist in nature in all kinds of interesting ways. So I strongly recommend you look it out, check it out. Be careful though too, because you're going to notice a lot of God talk in some of these other videos. So you know, this one's good, but it turns out that people tend to want to invoke the supernatural with this spooky sequence that seems to have all its application in the real world, and I don't think that's really necessary here. Just know that, you know, when it comes to the meaning of this, I mean, we are not only discovering math, but we're writing it, and it's just a powerful tool that allows us to then sort of just be able to describe the properties of nature, which is extremely interesting. So check it out. And here's one more that I would recommend: the Fibonacci sequence, Nature's Code by SciShow. That's a really good one to explain this. So check out this one and Vihart's video for sure if you can.